afternoon, everybody, and welcome to Solmax. Thank you for taking time out to join this webinar today. My name is Doyin Adesokan, and I'm the technical manager at Solmax. I've held this position for over a year now. I come into this role from an engineering background. I'm registered with the Association of Professional Engineers and Geosciences in Saskatchewan, Canada, and I will be your host for this webinar today. We rolled out this webinar sessions last year as a way to connect with the industry to share helpful, reliable, factual, unbiased technical information that will help with designing with geomembranes and designing with geosynthetics in general. We have 4 webinars already. All of them are available on our website, and they are available in the technical information section of the website. We have one on manufacturing methods of geomembranes. We have one on the resins and the additives. We have one on conductive back geomembranes, and the most recent one was on the cost-effective polyethylene materials that you can deploy on your site to reduce wrinkles. So today's webinar, we'll be looking at designing for success. So how can you design your geomembrane to do what it's supposed to do on a site? We'll take a look at 10 design missteps that we sometimes take that could affect the performance of a geomembrane in service. This webinar will be available for all attendees, and it will be available also on our website. The video will be available, and it will be available in PDF format as well if you want to review it later on, or if you have some comments or questions later on. We will take questions throughout the webinar, but all of them will be addressed at the end. So an outline of the webinar today, I'll go through a few background information that's going to help us transition into the 10 design missteps I'm going to be talking about. So we'll look at what geomembranes are, why do we need geomembranes, what's the key factors to consider when you want to select a geomembrane for a site. And when we say performance of a geomembrane, what does that look like, or what should we be expecting? And what are the typical resources that we need when we design with geomembranes? And then from there, I'll go into the 10 design missteps, go through all of them, conclude, recap, and then we take the questions and answer and discussion or comments at the end. So the first background information that I want to look at is geomembranes. So what are geomembranes? I've got a prop here with me to show you. Geomembranes are flexible polymeric materials that for all intents and purposes, they're considered impermeable. They use as covers, they use as liners in various applications. Some people call them liners just because they're widely used as liners. Some people call them cover liners. Some people call them flexible membranes or membrane sheets. So any material that's the polymer that can be used as an impermeable barrier system is a geomembrane. So why do we need geomembranes on our site? To contain. The primary function of a geomembrane is containment, to intercept the flow of fluids, to create an impermeable barrier or lining system for any application that we're trying to contain the fluids, in. So we want to prevent the release of unwanted fluids into the environment, so chemicals or leachates or gases. We want to prevent the loss of those materials or fluids that we want. So say water, so we want to cover up a reservoir so we don't lose water. Or at the bottom of a heap leach pad, we want to line it with a geomembrane so we don't lose our pregnant leach solution or all the ponds that we have on the site. So we want to protect what we want in that case. In some instances, we may want to keep our waste dry. So say you have waste rock on a mine site and you don't want air and water to get in, because as soon as you have air and water in that waste rock, you're going to have more problems. You're going to have acid mine drainage. So to prevent that from happening, to keep the waste dry, we sometimes cover it up with a geomembrane. So those are a few reasons why we use geomembranes on a site. So I'm going to show us a few applications now where a geomembrane or geomembranes may be used. So I've got a picture on the slide there. It's for a mine tailings pond. That's one of the widely used applications for geomembranes. And then we've got evaporation ponds, so saltwater evaporation or reverse osmosis, landfill lining too. we've got coal ash ponds, we've got landfill capping, biogas collection, sewage lagoons, sludge disposal, secondary containment, so at the bottom of your tank lining for primary containment, and then we have wastewater ponds. So those are some of the few practical applications where geomembranes are used. So what is the main factor to consider when we want to select a geomembrane for a site or for an application? The main consideration is the performance of that geomembrane under the expected site conditions. I know sometimes we tend to see a geomembrane as a commodity whose selection has to be based on price, but that shouldn't be so. We should look at a geomembrane based on the actual conditions under which it's going to perform. The performance of a geomembrane is a measure of what we expect it to do under certain conditions versus what it actually does under those conditions. And I'm going to use an example of a swimmer in this instance. So let's take a good swimmer for an example. The swimmer can complete several laps in a pool within record time. So if we now take that swimmer and we put him or her in a different pool and increase the temperature of that pool, say to boiling point, 100 C, 212 Fahrenheit, pour some chemicals, some acid into that water, or some corrosive chemicals into the solution, or say you decrease the temperature of the pool to freezing point or below freezing, and then you ask the swimmer to complete the same number of laps in that pool under those conditions as it would in a regular pool. I don't think that swimmer will be able to do that. The swimmer hasn't changed, it's still the same person, but the conditions under which you want him to give you this output now has changed. Right, so unless that swimmer has the right equipment or the right clothing or training to perform or to swim in those kind of extreme water pool conditions, it wouldn't be able to do it. And that's the same thing with a geomembrane. So the geomembrane should be assessed not just based on cost or price, but based on the expected site conditions. So the site conditions such as the chemicals that the geomembrane is going to be exposed to, the applied loads, the materials that are going to be in contact with the geomembrane at the top and at the bottom, the operating temperatures, the subgrade temperature, the slope, the duration, how long do you want it to do the job for? Those are a few things that we should consider. So what does the performance of a geomembrane look like, or what should it look like? It's the difference between what you expect and what actually happens. So what you expect is the picture on the left where the geomembrane is laid flat, intact, smooth, no damages. But in reality, if the geomembrane is not compatible with the site conditions, what you will get could be what you have on the right there, a geomembrane that's fully cracked. Another example is you expect the geomembrane, or you designed it to be a liner in a system. However, because of some site conditions that weren't considered, that liner geomembrane ended up being a cover, an inflated cover. If that geomembrane doesn't have a material properties to be a cover, it's only a matter of time before it actually ruptures. Or say in a heap leach pad now, you have a geomembrane at the bottom of your pad, and then you put your waste rock on top of the material, and you expect the liner to be intact under the load of the waste rock. But what actually happens is, if that material is not compatible with the applied stress or with your the subgrade, overliner, or the underliner, what you might get is a liner that's severely stressed or strained, or may even be damaged. That's the picture at the bottom right there. Or another example is you have a solution, a corrosive chemical or a solution or a high temperature solution, and you want to contain it. So you expect that your liner is going to be intact for the entire service life of that application, but because you haven't checked the temperature or the chemical compatibility, what actually happens is you have a liner that is softened or ripped or attacked by the chemical, and it won't do what it's supposed to do. So those are a few pictures to give us an idea of what a performance of a geomembrane could look like versus what we expect versus what actually might happen. So now I want to go through a few of the resources that are available for designing with geomembranes. And I need to go through this because I will be referring to them when I talk about a 10 design missteps. So I've got 8 points on my screen here. There could be a little bit more, but these are the main ones that we typically use. The ones that are in blue and bolded in blue, I will talk about those in more details in subsequent slides. So the first resource that we typically use, or the first one on the screen there, is the industry standard and specifications. So we have the ASTM standard for North America, and then we have the ISO standards for Europe and some other standards across the globe. Some of us are familiar with ASTM standards. ASTM standard, those are that's the body that creates the test methods for almost anything in our world today. ISO is also similar. The GSI is the Geosynthetics Institute. That's also a collection of, it's like a collection of individuals. It's an organization that critiques geosynthetics. So they have a section where they do geosynthetics research, and they do testing, and they write specification, and they write design guidelines and technical notes that are all there to help us with designing with geomembranes. And then there's FGI, that's the Fabricated Geomembrane Institute. It's similar to the GSI, but it's a little bit different. I'll explain all of this later on in a few slides. So the second one is regulatory standards and technical guidance documents. So these are those regulations that each jurisdiction might have. So maybe a state or a province or a country. They would vary with the jurisdiction, and they will vary with the application as well. So sometimes there's a specific liner material thickness that could be specified for, say, a subtitle D landfill, another one for a subtitle C landfill, or a liner for a cover application, and another one for an actual lining application. So these specifications are there as guidelines to help us with designing. The third resource is the manufacturer's technical data sheet and the technical information that we get from the manufacturer when we contact them. I'll talk about this more in a few slides. There's also index testing. The index testing is when you try to find the material properties of the geomembrane. You try to characterize it, how thick is it, what's the tensile strength, what's the tensile elongation, and all of those material properties. The conformance testing is similar to the index testing, but that's done by when the material is received on the site. So it's a way of checking the values that have been reported for the index testing. I'll talk about this too later on. And also there is performance testing. The performance testing is a little bit different from, apologies for that, it's a little bit different from the index testing. The performance testing simulates the site conditions that you're going to have. So the material isn't tested as an individual component. It's tested as part of a system or under some specific conditions that are similar to what you're going to have on your site. And there is pilot scale studies and test pads. These are similar to the performance testing, but they're like on a larger scale. So they simulate the conditions on a larger scale than what you would do in performance testing in a lab. And then there's published literature too. So these are all researches that have been done in the past, or textbooks, or journals, or articles. These are all some of the sources for our information for designing with geomembranes. So the industry standards and specifications now, the two main ones are the ASTM for North America and the ISO for Europe and like the rest of the world. There are various standards available, and the standard would depend on the parameter that you're trying to measure. So the standard for tensile properties is different from the standard for puncture resistance, which is typical with ASTM standards. And the test methods as well would depend on the type of the geomembrane. So the test method for a reinforced geomembrane will be very different from the test methods for a non-reinforced geomembrane. On the industry standards and specifications now, we have the GSI and the GRI specifications, guides, and practices. The GSI, which I mentioned earlier, is the Geosynthetics Institute. This is a collection of everybody who is interested in improving the usage and the purposes of geosynthetics in the industry. So anyone that has interest in geosynthetics, they're part of this organization. The Geosynthetics Institute has the research section where they test all geosynthetics, geomembranes, and the right test methods and specifications based on a benchmark value that they arrive at for testing different materials. So the GRI has industry specifications for geomembranes. The specification for geomembranes by the GRI is called the GRI-GM specifications. So for high-density polyethylene, the GRI has the GRI-GM13 specification. And then for the linear low-density polyethylene, they have the GRI-GM17 specification, and so on and so forth, the specifications for geotextiles and geogrids and all other materials too. Now the FGI is a Fabricated Geomembrane Institute, and they are very similar to the GSI, but the difference is they control flexible materials that you can prefabricate in a plant. So the GRI controls those materials that you have to weld on the field. The FGI controls those ones, or they write the spec for those materials that are flexible enough for factory fabrication. So PVC and other materials are under the FGI. They have their own specs too. So here is an example of a typical GRI-GM13 specification for high-density polyethylene. This spec has got the material properties of the geomembrane that have been considered to be useful for characterizing the material, right? And they have set the minimum values that has to be met by a geomembrane in this category for an individual thickness. So the properties they have on there, they have the thickness of the geomembrane. So you tell us how thick the geomembrane is, and then what is the sheet density of the geomembrane. The sheet density of the geomembrane will tell you if it's high-density polyethylene or if it's linear low-density polyethylene, and also the tensile properties. So we take a coupon from the geomembrane and we pull it till it fails. We measure the stress that fails it, and then we measure the elongation at failure. We measure the stress that causes it to yield. With high-density polyethylene, you have a yield and then you have a failure. So you measure the yield and you measure the actual failure stress and the failure elongation as well. We try to tear the geomembrane to measure the tear resistance. We measure the puncture resistance, try to puncture it with the standard equipment and see the force that's going to puncture this material. We test the stress crack resistance. For high-density polyethylene, stress cracking is the Achilles heel. So that's the routine property that has to be tested. So we take a sample, notch it in the middle or somewhere, apply some stress to it, dip it in a solution for a while, and see how long it takes for that geomembrane to crack. We take some other measurements as well to measure the durability of the geomembrane. We measure the oxidative induction time. This measurement is to assess how long it takes for oxygen or oxidation reaction to affect the geomembrane. So we take a coupon of that geomembrane, put it in the oven, heat it up to 200 Celsius in a nitrogen environment, and then we stop the nitrogen, introduce oxygen, and measure the time it takes for that oxygen, the time from when we introduce the oxygen to when the oxygen starts to attack the geomembrane. That's the qualitative, it gives us a qualitative idea of the durability or the quality of the material. So we measure all those properties, and the GRI-GM spec sets the minimum values that a material in the category has to meet. So the manufacturer's technical data sheet now, that's another source of information. This is typically based on the GRI-GM specification. So the technical data sheet for high-density polyethylene usually will reflect the values and the test methods on the GRI-GM specification. And the test methods are also completed as per ASTM standards. So the technical data sheet is very, very good for you to compare different materials, or say if your spec has asked for a non-reinforced material, you can look at the technical data sheet and the test methods and see if that's what you're actually getting. Or say you've asked for HDP, the technical data sheet can tell you if what you're getting is HDP and not LLDP. If you see a technical data sheet that has stress crack listed on top, then that should be an HDP material. If you see a material that has, let's say, 2% modulus, then that will be reflective of an LLDP material. So technical data sheets are very good resources for making sure that the material we've requested is what we have. They also provide some information on the test methods that have been applied to arrive at the values that are reported. So most of them have like notes at the bottom that show you if the test method has been modified or if a different test has been done. So the technical data sheet is a very good resource for that as a quality control, just to make sure you know what's going on with the material. And the values on the technical data sheet may meet or exceed the GRI-GM specifications. So at Solmax, we have materials that meet the GRI specifications. We have premium materials that exceed the GRI in some areas, and we have the high-performance materials that exceed the GRI in all areas. I'll show you an example later on of the stress-correct resistance of our high-density polyethylene series and how they vary for each of the categories of material, high-density polyethylene that we have. So now on index performance and conformance testing. Index testing, like I already explained, is when you take that material as an individual component and you try to identify the material properties. So you get the physical properties, mechanical properties, and endurance properties to characterize that material. The index testing helps you to compare apples to apples, the different materials on the same scale. Performance testing, on the other hand, is when you take that material and you test it under simulated site-specific conditions. So you have the subgrade that is close to what you're going to have on site. You apply the stress you're going to have on site. So it gives you a better understanding or a more reliable representation of the design life or the performance of your geomembrane under the conditions where you're going to use it. So unlike index testing that's routinely completed, you have to do it every time you produce a material, the performance testing is done on a case-by-case basis. So you wouldn't necessarily find performance testing results on index testing documents like the technical data sheet or the GRM-GM spec. Conformance testing now is similar to the index testing. It's the testing that is done when the material gets on the site. So the quality control person or takes a sample of that material and they test it and they see if that material conforms to the technical data sheet of the geomembrane manufacturer, if it conforms to your project specification, and if it conforms to the industry specifications, say the GRM-GM 13. So those are a few resources that we have, and I will be linking back to all of these resources when I talk about the 10 design missteps. So what are the 10 design missteps that may affect the performance of a geomembrane in service? We've listed 10. There could be more. If at the end of the webinar there is something you're expecting us to talk about that we haven't listed today, you can bring it up and we'll have a discussion about that at the end. So before I start talking about the design, the missteps now, I want to go through this report card that I have on the screen here. That's a summary geosynthetics report card that was presented by the Geosynthetics Institute in March at GeoFrontiers. And what I did was I took a picture of the presentation slide, and that's what we have on the screen. I'm one of those guys that go to a conference with a fully charged phone just so I can take pictures of slides during presentations and the like. So this report card shows where we are, where everyone is at in the industry. So they looked at different aspects of the industry from manufacturing to regulations, and it gave everyone some grading and some comments too. So they looked at manufacturing and said, they gave us an A grade. What they said is problems are immediately corrected. And then they looked at design, and the grading was between A to D. So some did very well, or some are doing very well, and some still have a lot of catching up to do. And hopefully with some of the information that we're going to share in this webinar today, we can improve some of our design strategies to improve this grading going forward. They looked at index test methods, and they gave it a B. What they had said was there needs to be more harmonization between the ASTM methods versus the ISO methods. They looked at performance test methods, and they gave it a D. And the comment was there is lack of engineering input. So engineers aren't doing so or as much performance testing as they should be doing. So there's still a lot of work that we need to do. There's still a lot of room for improvement in that area for geosynthetics usage. they looked at generic specifications. Now, generic specifications are like the GRIGM industry specification, or all the specifications that we have in our jurisdiction or province or state, that just guides how a certain application or the guides a certain project that you can't really do much about. And what they said, they gave it a C grading. They said it's needed for consultant because it's good, it's available, you can easily just consult it or use it, but it stifles innovation. So using the same material, a specific generic material for all applications, is not good for innovation. And it's not just innovation, it's also not good for the performance of the geomembrane in service. And I will talk about this as we go on in the design missteps. So they look at the other areas too. Inspection and installation, but the main area of this focus are the ones that have to do with the design aspect. So the first design misstep that I want to look at today, or that I want to address today, is the issue of relying solely on the technical data sheet from a manufacturer. The technical data sheet from a manufacturer is a very, very good resource for making sure that when you've requested the material, you're getting exactly what you've asked for. You can look at the material properties and see the values and see if it corresponds to what it should be, right? So it's very good for that, but it's not enough to tell you how your material is going to perform on the site. And the main reason for this is when the index testing for characterizing material is done, we just do it on an individual component. So we test this material as in isolation outside of a system. In reality, any geosynthetic material, not just geomembrane, they are part of a system, of a larger system. So there are conditions to consider. There's the environmental conditions, the subgrade, the loading, and so many other conditions. So relying on a technical data sheet won't tell you or won't give you a good representation of field performance or service life. So it's essential for you to complete performance testing under the expected conditions. We have a performance testing program that we run at Solmax. I will talk about this later on. Another reason why it's not good or good practice or a very good idea to just rely on a technical data sheet and take a manufacturer's technical data sheet just as it is there are some marketing tricks and gimmicks that you can find on technical data sheet. There's a lot of play on numbers sometimes, and a lot of play on the test methods too. So say the tensile test method now, you're supposed to measure to pull the geomembrane at a certain gauge length. Some manufacturers may change the gauge length just to pull the geomembrane more so that it can report a higher value. So it doesn't really reflect it's not really good for comparing apples to apples, or sometimes too, you may have values on a technical data sheet that don't even belong on there. So someone might report a value for a reinforced material when what you've requested is a non-reinforced material. Of course, the values are a bit different, but if you're not familiar with a technical data sheet and if you don't know what you're looking for, you just look at the two technical data sheet. Oh, this one has a higher value, that one has a lower value. You throw the other one out. So relying just on a technical data sheet is not enough. It's not. We should do more. We should do our own performance testing to actually understand how those materials will behave in service. The second point is relying on conformance testing for performance. So some people go, oh yeah, I know how to catch a manufacturer's tricks. I'm just going to make sure I do conformance testing. That's very good. That's good practice. It's essential. It's a good quality control practice. And conformance testing, I'll just go over it again. That's when you take the material when you receive it on the site and you repeat all of the index testing on the spec, on the technical data sheet, and see if it's actually what it should be, if it's what the manufacturer said it is, and if it complies with what the GRM spec or whatever spec you're using, if it complies with that, right? So it's a good practice, but again, you're repeating index testing. You're testing the geomembrane in isolation as an individual component. It won't tell you the performance of your material. It's still essential to do performance testing as well. Test the geomembrane under the expected conditions. The number 3 point is relying solely on generic specifications. Having generic specifications are good. They're a good way to start. They're a good starting point. but these are usually the minimum that you have to meet. It's just like any code out there. A code is a minimum requirement that you have to meet. So there are two aspects that I want to look at for this generic specifications today. I want to look at the GRM-GM, and I'm going to look at the regulatory generic specifications. So specifying the GRM-GM requirement for all applications, it's convenient, but in some cases, you may need more than a GRM-GM material. So having one liner for all applications may affect the performance of that liner in service. I'm going to use an example of this 4 vehicles that I have on my screen here. So let's take that top one, the red one at the top there. So you have this nice, cute Sunday vehicle that you can take out for shopping or a few road trips or do a few things. It's very good for that. It does a good job. Now, if you want to go off-roading and you take that car and put it on an off-roading site to do off-roading, I don't think that car is going to survive that condition because it's not designed for off-roading. It doesn't have the suspension to do the job. It doesn't have the engine. It doesn't have the tires. It's not built for that. You need a vehicle that is designed for off-roading to go off-roading. And similarly to, say you want to go to a Formula One racing track, that's the picture on my bottom left there, or you want to go do NASCAR racing or whatever other racing that you're more familiar with, that red car isn't what you will put on that site. It's not built for racing conditions. It doesn't have it's not designed for that. Trying to ask that red car to do the job of a racing car is asking for too much. And that's the same thing with specifying a GRI-GM material for all applications. It's in some cases, we may be asking that material to do too much. So we need to understand the site conditions and find the material that meets the needs of the site. So still in generic specifications now, the GRM-GM one, here is a comment that I got from a senior engineer regarding this topic. And he had said that we need to understand that the superior properties of even a slightly more expensive material may help you improve the overall project economy in the short term, in the long run. It may help you reduce the maintenance that you would have on that geomembrane. It would increase the durability and service life of that geomembrane for the entire service life. So you may be spending a little bit more now, but eventually the gains will be really, really high for you. And here is a picture here. I'd mentioned I was going to show you a picture of how some of Solmax's materials compare. Here is a picture of the stress crack resistance of Solmax's different high-density polyethylene materials. So we have materials that meet the GRI-GM spec. We have materials that are slightly better, significantly higher than the GRM-GM spec. That's the Solmax Premium. And we have the Solmax's Goliath geomembrane that just towers above all of them, that exceeds the GRM-GM spec significantly. So for a parameter like stress crack resistance, which is critical to high-density polyethylene, depending on what your application is, you may need to go really, really high with your material selection in that instance. So the second aspect of the generic specification I was going to look at is the generic regulations for all applications. So unlike the GRI-GM specification that is within our control, these generic regulations are usually outside of our control. We can't really do anything about it. It's like our hands are tied. But so the message now is that there needs to be an improvement in regulatory specs. So there needs to be a room there that allows for performance-based testing. So there needs to be an addition to regulations that goes on, maybe says something along the lines of the materials that we have specified here are recommended, but if you can show based on performance testing that more or alternative materials may be suitable, then you can use those materials for your site. I think that kind of allowance or flexibility or robustness has to be included in generic specifications, just so we don't keep specifying the same material for all applications, and just so we can introduce more performance testing to find exactly the best material for our site. The number 4 point or misstep I want to look at is reproducing an existing spec for a different project. I know that sometimes as engineers or designers or specifiers, we want to get the quotes and tenders done quickly. And sometimes the difference between getting a job and losing the job is how quickly you can get that done. So you don't want to spend too much time on having to write a new spec. It's convenient to use what you have and just throw in a factor of safety. Yeah, call it done. It's a convenient practice, but it's not necessarily good for performance of the geomembrane. You might be over-designing. You might be using a material on the site that you don't really need. Or, on the other hand, you might be under-designing, which is the bad one. So you might be putting a material on the site that isn't suitable for that site. So it's essential to look at your sites and understand your site conditions and find a material that meets it. As much as we can, let's try to avoid reproducing an existing spec for a different project without actually digging deep to see what we really need. Number 5, not planning ahead and not having materials pre-selected and pre-tested for expected performance. So there are 5 P's on there. Proper planning prevents poor performance. Those are 5 P's that are applicable to life. They're applicable to geomembranes as well. It's essential to have materials pre-tested and pre-selected. But the 3 main testing that should be done are the chemical resistance. So pre-test your material for chemical resistance, especially in those critical applications. It's not enough to just go with a generic chemical resistance chart. Actually have that material dipped into the site-specific chemical or the most critical one that you're going to have on the site. Also, do puncture resistance. That's another source of damages to geomembranes. Apply the loads that you're going to expect, or add some factor of safety to identify the worst-case scenario. Do interface your resistance as well. Don't just take the values on a chart or in published literature. Do the actual specific testing that you need on your site. Have this done before you select your material. Planning is key. It's when you pre-plan and you pre-test the material, you have a good understanding of why that material has been selected for that site. So say in the future, down along the line, if people start giving you pressure, if there's a need to cut budget or a need to change schedule and they want to save some money and they start pressurizing to change the geomembrane or the geosynthetic material, you can push back and say, I know what the material is there, that's not going to change. Or if it's going to change, you know the exact performance that you want that material to meet. If you haven't pre-tested and pre-selected the material, then you can just pick anything and just go with it. And that's, in picking anything, that's when a liner might fail on the site. I've got an extreme example on there that, so an example of, say, your colleague comes and tells you, oh, we can save some money on some liner, and I've got some heavy-duty construction bags that you can glue together and use. That's extreme, but it's just an example to show you that when that pressure arises that wants to push you to change your material, having pre-tested and pre-selecting your material is going to help you push back against an inferior material for your site. So it's essential to have this proper planning ahead of time. Number 6, not involving the manufacturer in the design. This is important for us to know. Manufacturers know plastics, and we have the interest of the project at heart. It gives us a lot of pride when we know that our material is lasting and doing what it's supposed to do. We put a lot of effort, a lot of research, a lot of input to make these materials durable and high quality. So we want them to be used the way they're supposed to be used. So we know those plastics, we know the resin, we know the formulation, you know your site, you know your design. So it's essential for you to work with a manufacturer, work with us to help you find the best material that's going to achieve your site objective. There's a tendency for engineers or owners and users or the industry to try to pull away from manufacturers because you don't want a manufacturer to oversell you their capabilities. That's fine. That's a legitimate concern. If you feel like a manufacturer is overselling their capabilities, speak to another one. Speak to several of them and compare. Collect all their samples and go test it yourself and see. But it's essential to work with the manufacturer. Ask them questions. We've been involved in so many of those projects. We can give you a few tips here and there. And still on that point, I mentioned earlier that we have a performance testing program at Solmax. So I'm going to talk about that in details now. So this performance testing program was rolled out so we can walk the walk and talk the talk, because we believe in performance testing. We don't believe in just relying on index tests or technical data sheets. So we put this program out there to help our clients with your material selection process. And what we do is we test different materials that we think should be suitable for a site. We test them for chemical resistance, puncture resistance, interface shear resistance if it's needed, and then we make this available to the client to make a final decision. It's available at no extra cost to a client. It's not going to cost you anything, and you don't even have to purchase material from us. No purchase is necessary. What we ask from you to do this testing is to give us the details of your site. So send us your samples from your site. Send us your subgrade sample. Send us the overliner sample. Send us your foundation conditions, and speak to us and see how we can do this testing for you. If you're not able to send the actual site materials to us, then give us enough information that is going to help us reconstitute those materials in the lab or in a test kill. So send us the gradation curve for your overliner or your underliner, or for your subgrade. Send us the liquid limit of your clay or whatever material, whatever information you're going to send us, the USCS classification that's going to help us reconstitute this material. It's better for us to have the actual site material so we can test it correctly, but if you can't, due to whatever reason, logistics or anything, then give us enough information and we will reconstitute this for you. Also for example, your compaction, send us the optimum moisture content, the compaction effort that we should apply, the dry density, we will compact this for you. This program has been widely successful. Engineers love it. Owners love it. We've used it on several projects. There's a good case study on our website that you can take a look at and see how it's worked for a heap leach mine project. And there are other case studies too that we can share with you if you want some more information on that. And also, one of the projects that we did, this was the puncture resistance testing. So you can see the soil in the test cell. We tested a few of our geomembranes. They gave us the applied pressure that we're going to expect on the site. We added a factor of safety of about 2.5, so worst case scenario. And then we gave them this result, and they were able to make their own decision based on the result that we shared with them. So the number 7, not knowing your site or service conditions fully. This doesn't happen often, but when it happens, it's usually catastrophic. It's like having a vehicle that doesn't break down, but then when it breaks down, it's like, oof, a lot of money. So usually people know their site, but sometimes they miss a few things. So you have to fully understand your site conditions. We can't stress that enough. Know the chemicals, know the applied stress you're going to have, understand your slope. If you're going to have a 3-to-1 slope, know you're going to have a 3-to-1 slope. Don't let surprises happen that could affect performance. Here is a picture of a landfill where the applied stress on the liner was underestimated during the design. So they overloaded the liner, they put the waste on there, and the yield stress and the failure strength of the liner was exceeded, and the liner ripped in the middle. So it's essential to know what you have on your site. A couple more examples of this on the screen here, where if you don't understand your groundwater level, or if you don't know that your groundwater level is going to change and you haven't made plans for drainage, you're going to end up with a whale or with a bubble. And a material that's blown up like that, if it doesn't have the multi-axial properties to do that, it's only a matter of time before it actually ruptures. Also for gases too, so you probably didn't know you're going to have gases on your site, you missed that, so you didn't plan for venting, you might end up with bubbles that could damage the performance of the geomembrane. Number 8, geomembrane incompatibility with the site conditions. This has to do more with the mechanical and physical damage. So when your geomembrane is not compatible with your overliner or your underliner or your foundation conditions, there are charts in the literature that can help you narrow down candidate materials, but don't just go with the chart. Also follow up with your site-specific testing. So an example of the chart is this one that I have here on the screen. And at the bottom layer, at the bottom level, if you take a look at that one, that's for if you have a soft foundation, a fine-grained overliner, a fine-grained underliner, and whatever stress you're applying, there's a recommended material. And in this case, they've recommended LLDPE. So you can narrow down that LLDP now and then test a few LLDP products as to the one that does the job best for you. So compatibility with the site conditions is essential for performance. Poor designs. This one basically explains itself. So not making adequate considerations for, say, the geometry of your facility, or the slope, or the interface materials. The picture at the top corner is for a slope that failed. So the slope failed under the geomembrane. If that geomembrane is not designed for differential settlement, if it's like a stiff geomembrane, it will be a matter of time before it actually starts to crack. And also, your runout or anchor trench design, if you haven't made enough consideration to design properly and you apply too much tension to your geomembrane when you're doing your anchor design, it might cause it to fail in service. And other aspects too, like the geomembrane type or the geomembrane thickness, or if you haven't designed your site well for leakage assessment too. I'll talk more about that leakage assessment now. So relying on a single liner system instead of a composite system. A single liner system is when you have a geomembrane directly on top of your subgrade. So if there's a leak in that liner, it's going straight into the environment. A composite system is when you have a geomembrane and a compacted clay liner, or you have a geosynthetic clay liner under. So you have a double kind of like system trying to prevent leakage. So if there's a leak in the liner, there's a second backup under it. A double liner, a double barrier system is when you have a primary geomembrane layer, you have a leak detection layer under that primary geomembrane, then you have a secondary geomembrane at the bottom. So you have a two-layer system. So if there's a leak in the primary geomembrane, it doesn't go into the environment, it goes into your leak detection layer, and you can collect that and have that fixed before the geomembrane damage deteriorates into something that's excessive. So incorporating this kind of design strategy into your specification or construction work is going to go a long way in preventing leakage. And here is a picture on the screen of a double of 287 double-lined landfills that were sampled, and one of them, the one on the left, had a sand leak detection layer between the primary and the secondary geomembrane. The other one had a geonest leak detection layer. And what they had found was that the geomembrane alone system wasn't able to reduce, wasn't sufficient on its own for preventing leakage. The geomembrane with a composite system with a CCL, compacted clay liner, didn't make too much difference. It was pretty similar to the geomembrane alone. The one that achieved the most leakage reduction was the geomembrane in contact with the GCL. So it's essential to understand how this design aspects work. And there are a few design calculators out there. The most popular one is the landfill design application site. It's free of charge. It has calculators for slope, for interface shear, for puncture protection, for thickness, for leakage assessment. So you can use this kind of calculator as a first step for you to estimate the parameters or do an initial assessment of your geomembrane. After using a calculator, you can then go on and do more rigorous calculations later on. So number 10, not planning for leak location. That is a number 10 misstep that we have found. A senior engineer once said to me that all boats leak, but they have a system that keeps them afloat. So the boat has a pump system or a bilge system and some other sensors in them that detect leaks and help them to find those leaks and keep the boat from sinking. This is similar to geomembranes too. Despite all the good efforts from manufacturing, the rigorous testing, to leak location, to careful installation, to careful backfilling, damages happen that can cause leaks in the geomembrane, and that point is also reflected in the notes by Ian Peggs in one of his texts. And he had said that even though we know that we can build non-leaking facilities, it's possible for a geomembrane not to leak. However, damages happen, and we should consider this unavoidable. So the next time you want to specify a geomembrane, just have it at the back of your mind that damages can happen. when a geomembrane is not damaged, it's impermeable, but because of that damage, you can have a leak. So go into your design with that mindset and have the right tools in your design that is going to help you find leaks. It's going to help you catch the leaks before it deteriorates into something really, really bad. And these tools are available. It's not like we're just going to start researching to find them. They're available. So why are we not using them? I'm going to go through a few of those tools now. So the first tool here is start by carefully selecting your material. So instead of specifying a regular black geomembrane, specify a conductive geomembrane that's going to help you find leaks. And I'm saying conductive because the conductive overcomes some of the limitations we use in the regular geomembrane, right? And also, instead of having a black regular geomembrane, specify your geomembrane in white. And the reason for that is the white is going to be a good visual detector for you. So if you see black coming through a white liner, you know there's a damage somewhere. When you specify those materials, also specify leak location surveys in connection with this. It's not enough to specify a conductive geomembrane and not have it leak tested. So specify leak location after installation, specify leak location after backfilling. Incorporate good designs as well. So combine those two with careful design. So instead of using a single liner, instead of just placing your liner on a subgrade, do a composite system. Put a compacted clay line, or a GCL under, and do a double line system too, and have a leakage detection system in between the primary and the secondary geomembrane. That's a good design. In addition to that, add some leak monitoring systems as well. So you can have wells or whatever leak monitoring system that might be suitable for your site. This idea of leak location or planning for leak location has to be understood by everybody. So not just the installer, not just the designer, the owners too, especially the owner. So it's our duty as engineers to help those owners find the best solutions. So let's specify those tools. Let's incorporate those tools into our specifications that will help us find leaks. All of those tools are very similar to the sensors that we have on our vehicles today. Most vehicles today have forward collision warning, lane departure warning, lane change assist, automatic braking, right? It's not because manufacturers of those vehicles think that drivers are becoming sloppier or drivers are becoming careless. It's because they know that even to the best drivers, damages can happen, errors can happen. It takes a little bit of distraction, or even if it's not your fault, there's somebody beside you who isn't paying attention. When you have that sensor, you can make precautions, right? I've got one of those sensors in my car that every time I cross the yellow line, it just goes off like a frog croaking, and then I just pull back. So it's very good. Having a conductive liner and not specifying it on your site is like having all the sensors on your vehicle and turning everything off. You're not doing yourself too much good by not using the sensors that are going to help you prevent an accident on the road. So it's essential to incorporate the right tools into our designs. So in planning for leak location, again, specify a good material that's going to help you find leaks, have it tested after installation, have it tested after backfilling. Talking about this to testing now, one of our installers, speaking to one of our installers, is actually watching this webinar now, and we had a discussion about that, and he said to me that isn't it redundant to do both? So you do spark testing and then you do dipole. And I said, yeah, it's redundant, but it's good redundant. Having a material tested for leaks after you've installed it is a good way for you as an installer to show that you've done a leak-free job. So you can sign off on that and know that you don't have to worry about anything too much. So, but depending on the budget, depending on what is available, you can do both or you can do one. If you have to choose one, then do the dipole survey. So to conclude now, designing for a geomembrane or designing a geomembrane for performance is not just digging a hole, throwing a black plastic inside, getting a 20-year warranty or the highest warranty you can get, filling it and forgetting it. There are steps, there are practices, there are established procedures to follow to have this geomembrane do what it's designed to do, which is to contain. So to recap all of the points that we've gone through today now, to ensure that your geomembrane performs in service, to ensure that it contains for as long as you want it to do that for, Number one, do not rely solely on a technical data sheet from your manufacturer. It's good information, but it's not going to tell you how your material is going to perform on your site. Do not rely solely on conformance testing. Do your performance testing as well. Do not specify, do not rely solely on generic specifications, or do not specify generic materials for all applications. So the GR and GM, don't specify that for all applications. Look at your site, understand your site conditions, and find the material that's going to help you achieve what you need on your site. As much as you can, avoid reproducing an existing spec for a different project. Site conditions can vary widely. Plan ahead and have your materials pre-selected and pre-tested for expected performance. Number 6, involve the manufacturer in your design. We have the best interest of this project at heart. We want these materials to succeed. We want them to do what they're supposed to do. So work with us. Let us understand your design. What are you trying to achieve? And then we can use like the performance testing program to help you find the best fit material. Number 7, know your site and know your operating conditions. Number 8, select your materials carefully and ensure that your materials are compatible with your site conditions. Number 9, your designs too. A single line system may not be excuse me, may not be sufficient. You need to use a composite liner or a double line system with an allowable leakage rate. Number 10, incorporate the tools that are available to us for finding leaks after installation and in service. So to conclude now, every geomembrane should be evaluated for its site-specific performance, not just in cost. The use of a one-size-fits-all geomembrane for all applications should be avoided. It's not good for performance. All generic specifications are the bare minimum. There are so many materials out there that exceed those bare minimum. Look for them, find them, place a demand on your manufacturer, and see what they can do for you. Incorporate design practices that would help this geomembrane succeed, right? So it's not enough to just hope that the geomembrane will succeed or wish that it will succeed. We need to consciously help this geomembrane not fail. Let's not set this geomembranes up for failure. Let's help them succeed. Let's use the right tools. And if you have any question on design or writing a spec or on the performance testing program, you can speak to us. Speak to me. You can send us an email at tsvoren@solmax.com, or you can send me an email directly at d@solmax.com, or you can give us a call as well. On that note, I'd like to say a very big thank you for this webinar today. Thank you for your time. The webinar will be available online afterwards in both the video copy and a PDF copy. A PDF copy will be sent out to everyone in the webinar, and we will take questions now or comments or some discussion. Thank you. So I've got a question here. Are the slides available for download? Yes, I will send the slides to everyone today. You will get a copy, and also they're available. They will be available on our website later on, and so also the other webinars that we've had too. They're available. What timeline would you recommend for engineers to contact Solmax to designing with geomembranes? How much lead time do they need for the information? Eric, that's a very good question. Thanks for that question. We want you to contact us as soon as possible. It's never too early. The earlier, the better. In fact, before you write the spec, it's going to save us time. We don't want to refine your spec. It's better for us to involve us when you start thinking about the project. So at the project initiation stage, when you start bidding or even before that, as long as you get hold of the information that you need for that project, send it to us before you even start writing the spec. It's always better that way. If there's a point that you think we should have mentioned and we didn't discuss today, you want to ask us about it, you can bring that up too. Or if you have any comments or any position or opinion that's different, we can talk about that too. Okay, so a feedback form. Oh, we do have a question here. Let's hang on here. How can specifiers protect that installers are correctly installing systems for the best quality? Is there anything beyond CQA that should be discussed? That's a really good question. But the main thing that we have is still the quality control. Like, it's just about ensuring that someone is watching. All those damages happen when someone just turns their back. So the main thing that we can emphasize is construction quality assurance. Just keep an eye there. From a manufacturer's perspective, we have our installation guidelines that we recommend. However, we can't really enforce that if there's no one there to make sure they're doing what they're supposed to do. Okay, another point that I've just that we could consider too is the experience. So they have to be certified by Yagi too for them to do what they're supposed to do. So look at what people have said about them. Look at the jobs they've done in the past. But in addition to that, even the best installer, if they have a bad member of a crew on site, then things can still go wrong. So it's still essential to have a good quality control person on there, keeping an eye on them. So maybe to add to that number 3 question. So for specifiers then, when you write your spec, maybe write a spec that says your quality control person has to be there all day. You know, write something into the requirements that keeps them on site and keeps them watching. Maybe the frequency of inspection or something that just so they can catch what's going on. Okay, so there's going to be a feedback form or request that will be sent to everyone today. Can you please take some time out to fill that back? We want to improve our webinars. We want to improve the information we're sharing. We want to make sure we're meeting the objectives of those webinars. So give us your feedback. And again, we'll thank you for joining us today. It's been a pleasure. We hope to see you again, and we hope that you keep up with all of our activities at Solmax. Thank you.